Good day everyone. I am Samrod A. Gawad and today let's talk about the boundary layer concept and thickness. First, what is this boundary layer? Boundary layer is a thin fluid layer which is formed on the surface of an object moving across the fluids. This boundary layer is created due to friction between one fluid and the moving surface. If we consider an aircraft on flight, the boundary layer have an impact on the skin friction, driving, stall, and the let transfer on high-speed aircrafts. The boundary layer concept. The boundary layer concept describes a thin region near a solid surface where viscous forces significantly affect the fluid flow. So what is this viscous forces? Viscous forces is a measure of a fluid resistant to flow. Like for example, the glycerine moving slowly.
Boundary layer thickness is the distance from the surface where flow properties reach a certain percentage of free stream value. There are two types of boundary thickness, the displacement thickness and the momentum thickness. Displacement thickness quantifies the outward shift of streamlines due to the boundary layer, effectively making the body appear larger to the outer flow. So, it means the displacement thickness is the imaginary distance by which the outer flow streamlines would have to be displaced outwards to compensate for the reduced mass flow rate within the boundary layer. It represents the thickness of the fluid layer that would have been present if the boundary layer wasn't there. So, the example of displacement thickness is, think of a river flowing over a rock. The water near the rock surface slows down due to the friction. This creates a boundary layer to maintain the same flow rate as if the rock wasn't there. The water flow farther away from the rock needs to be pushed outwards, effectively making the rock appear larger. This outward displacement is the displacement thickness. And the second one is the momentum thickness. Momentum thickness measures the boundary layer effect on momentum, representing the distance the surface needs to be displaced to account for momentum loss. Momentum thickness represents the imaginary distance by which the surface would have to be displaced inwards to compensate for the reduced momentum flux within the boundary layer. In other words, it's the thickness of the fluid layer that would have been present if the boundary layer wasn't there in terms of momentum. So if the displacement thickness is displaced outwards, while the momentum thickness is displaced inwards. So, the example of momentum thickness is, consider a flat plate placed in the flowing stream of air. The air particles touching the plate slow down, forming a boundary layer. The momentum thickness represents the distance by which the plate would need to be moved inwards to compensate for the reduced momentum within the layer. This inwards displacement would effectively reduce the plate size, resulting in smaller drag force.
Ever wondered why some fluids move so smoothly while others creates chaos? The answer is boundary layer. If we talk about boundary layers, may be either laminar or layered, and turbulent or disordered, but depending on the value of Reynolds number. This concept was first studied by Osborne Reynolds over a century years ago. In laminar flow characterized by the smooth, parallel movement of fluid particles. Laminar boundary layer is the laminar and the streamwise velocity changes uniformly as one moves away from the wall, as shown on the figure. It occurs when a fluid moves in a parallel ways with no mixing or turbulence between them. The example of laminar boundary layers is when the fluid interact to the pipe. So, the fluid in the pipes and vessels. So, when a viscous fluids such as water or oil flows in through smooth in a straight pipe with a low velocity, it is flows typically laminar. Highest Reynolds number, the boundary layer is turbulent and it's characterized by the unsteady or it's changing with the time. Means its swirling flows inside the boundary layer. And the external reacts to the edge of the boundary layer just as it would the physical surface of an object. So, the boundary layer gives any object with an effective shape, which is slightly different from the physical shape. That's why, unlike in the laminar, turbulent is a fluid motions characterized by its irregular and chaotic changes due to the pressure and flow velocity. Here's the example. The example of this is rivers and streams. Water encounters obstacles like rocks, trees, overbed, varying depth and shapes. Now, it creating waves and disrupting the smooth flow, leading to a turbulence.
What is a boundary layer? In fluid dynamics, a boundary layer is a thin layer of fluid immediately next to a solid surface. It is formed when a fluid flows past a surface and the fluid's interaction with the wall causes it to slow down or even come to a complete stop at the surface itself due to viscosity. Remember, it is not the entire flow near the surface, but rather the thin layer of the fluid that is immediately adjacent to the surface. It is the region where the fluid's velocity is affected by its contact with the surface. Now let us observe how a river water flow past a rock. As you observe, the water flows in two different ways, smooth and chaotic flow. But what do you think causes these two flows, the smooth and chaotic flow? These are caused by the laminar boundary layer and turbulent boundary layer. The water that is very close to the front of the rock and is flowing smoothly in layers like thin sheets of water sliding over each other. This smooth, orderly flow near the surface is a laminar boundary layer. In contrast is the water flowing past the side or back of the rock. The water is all mixed up and swirling around, not flowing in smooth layers anymore. This chaotic, messy flow near the surface is a turbulent boundary layer. Think of it like this. The water starts smooth, which is the laminar flow, but can become messy, the turbulent one, as it moves along the surface. At this moment, let us have our real-life example of laminar and turbulent boundary layer. We have here a mug and coffee, wherein the mug will serve as the surface and the coffee will serve as the fluid. Now observe how stirring the coffee gently and stirring the coffee vigorously will make a difference. If we stir the coffee gently, creating smooth swirls close to the cup, that's like a laminar boundary layer. The coffee is moving in an orderly way near the cup. But if we stir the coffee vigorously, making it all mixed up and chaotic near the cup, that's like a turbulent boundary layer. The milk is swirling and mixing a lot near the top.
Hello everyone, today we're going to dive into a key concept in fluid mechanics, the boundary layer separation. It's an important topic because it plays a significant role in how fluids interact with surfaces, and it affects everything from aircraft performance to automotive design. Let's break it down. First off, what exactly is boundary layer separation? In simple terms, it occurs when the smooth flow of air or fluid over a surface is disrupted, causing the boundary layer, which is the thin layer of fluid closest to the surface, detach. This detachment results in a turbulent wake forming behind the separation point. To give you a clear image, imagine wind flowing over a surface of an airplane wing or a car's body. If the airflow detaches, it creates drag and reduces efficiency. Now let's discuss what leads to this separation. There are a few key factors at play. First, we have the strong disturbances. Disturbances like the sudden deflection of a flap on an aircraft wing or the shock waves created by supersonic speeds can disturb the smooth flow of air and cause a separation. In cars, elements like side mirrors or spoilers can also create disturbances that disrupt the airflow. Next, we have the boundary layer type. The boundary layer can either be laminar or turbulent. Laminar flow is smooth and steady, like when a syrup flows over a surface, while turbulent flow is more chaotic. Next, you have the geometry. The shape of the surface is crucial. When the geometry changes abruptly, like the sharp trailing edge of the aircraft wing or a sudden curve in a body of a car, it causes the boundary layer to lose its adhesion and detach. That's why modern cars designs focus so much on aerodynamic to create smoother, more gradual curves that reduces separation. Next, we have the adverse pressure gradient. This occurs when pressure increases in the direction of the flow. For example, on an aircraft wing. If the air slows down towards the trailing edge, the pressure builds up, causing the airflow to separate from the surface. This is a classic example of how pressure gradient can directly influence the flow behavior. Now that we know what causes boundary layer separation, let's talk about its consequences. This is where it gets interesting because separation can have a major impact on performance. First, increased drag. One of the biggest effects of separation is an increase in drag. Take, for example, a truck driving at high speeds. The flow detaches from the rear, forming a turbulent wake. This wake creates a drag, which resists the motion of the truck and increases fuel consumption. In fluid mechanics, we study how to reduce drag by managing separation effectively. Next is reduced lift. In the case of aircraft, boundary layer separation can lead to a loss of lift. This is critical for keeping the plane in the air. If the flow separates too early, it disrupts the lift generating pressure distribution over the wing, and this can even cause the plane to stall. Understanding and controlling separation is essential in designing wings that maintain lift at the high angles of attack. Next is to reduce efficiency. Whether it's in a racing car, a sports bike, or even a golf ball, boundary layer separation impacts efficiently. In racing cars, engineers design aerodynamically efficient body shapes to minimize drag. The dimples on a golf ball are another great example. These dimples help manage the airflow and reduce the boundary layer separation, allowing the ball to travel further. So to wrap things up, boundary layer separation is a key concept in fluid mechanics that affects the performance of everything from airplanes to automobiles to sport equipment.
So in number 4, boundary layer fences. So we have here the two controls, the passive control and the active control. Let's talk about first about passive control. Passive control have the streamlining, turbulence, boundary layer fences, and sanction. So what is streamlining? streamlining is thus shaping the body to reduce the pressure gradient. So, ang streamlining daw is isa ito siya sa mga kagamitan ng pipe natin para makapagbigay or makapag-reduce ng pressure, and also nakakatulong din siya para mapabilis ang pagdaloy ng tubig sa ating pipe. And for the turbulence naman is introducing turbulence to the boundary layer to make it more resistant. So, ang turbulence naman daw is ginagamit naman ito siya para masigurado na yung pipe natin is strong or hard siya. And for the next is the boundary layer fences. Ito naman siya is yung mga small plate ito siya na naka-vertical, and then nilalagay ito siya sa surface ng ating boundary layer to separate or para ma-separate niya yung pagdaloy ng tubig. And for the last, sa passive control natin is the sanction. Sanction is ito naman siya yung may karapatan na mag-separate or mag-remove ng mga low energy sa fluid natin galing sa boundary layer para ma-maintain ang attachment ng ating pipe. So next is the active control. So we have here 3. The blowing, vortex generators, and surface morphing. So let's talk about first about blowing. Blowing is kumbaga ito yung ginagamit ng para pang-inject sa fluid natin para ma-increase ang momentum at saka mapa-delay rin ang separation. Next is the vortex generators. So what is vortex generators? Kumbaga ito yung mga maliliit na device na may kakayahang gumawa para mapa-enhance ang pag-mix at saka mapa-delay rin ang separation. And for the last in our active controls is the surface morphing. Surface morphing is ito yung naman yung may kakayahang magpalit ng shape sa surface natin para makontrol ang pagdaloy ng tubig sa ating pipe.
Good day everyone, Amari Esther Vita. Today, we will talk all about the drag reduction techniques. So what is the drag reduction techniques? So first is the reduction techniques, or the drag reduction techniques is aims to minimize the resistance an object encounters when moving through a fluid, and can involve streamlining shape, smoothing surface, using fairing, or employing active flow control system. We all know that drag is a force that opposes the motion of an object through a fluid, like air or water. And it's a type of friction arising from the interaction between the object's surface and the fluid molecules. And the drag reduction techniques ay binabawasan ang force or energy na nararanasan kapag ang isang object ay gumagalaw. For example, the airplane. So makikita natin sa isang airplane na maganda at maayos yung hugis. Maayos ang mukha ng isang airplane at balanse ang pagkakabit ng bawat materyales. Kaya kapag pinapalipad ng ating airplane, yung ating airplane maayos at balanse ang paglipad, at doon na papasok ang drag reducing. Nababawasan na ang paglipad ng ating airplane dahil sa force or energy na nanggagaling sa likod at harap nito. Kaya nababawasan yung drag or nire-reduce yung kanyang drag kasi nga doon na sa impapawid yung ating airplane. Kaya mas comfortable na yung mga tao doon sa loob ng airplane. Kaya nakakalipad yung ating airplane sa ating himpapawid. Here are some common drag reduction techniques. First is the streamlining shape. Refers to designing object to minimize resistant drag when moving through a fluid like air or water, achieved by creating smooth, elongated forms that allows the fluid to flow around efficiently. So, ang ating streamlining shape, ito naman yung parang gina-minimize niya yung shape ng ating objects. Like for example, the airplane. Tinitingnan niya ang disenyo ng ating airplane para mabawasan or bumaba ang drag kapag gumalaw ito sa hangin or sa tubig. Like for example, the airplane gina-minimize yung kanyang itsura kapag nandun na siya sa himpapawid para maging balanse yung kanyang paglipad. So, mag-imagine tayo ngayon ng itsura ng airplane. So, ang itsura ng airplane natin ay mahaba, makinis, 'di ba? And then, meron siyang mga pakpak. At yung paang mukha niya is parang oval na shape, pero parang ano lang siya, yung manipis. So, yan ang dahilan kaya nababawasan yung drag ng isang airplane kapag ito ay nasa himpapawid na. At because nasa himpapawid na siya. At saka, yun yung dahilan kung bakit meron tayong streamline na tinatawag kasi nga dito pa lang siya sa baba is ginaayos na yung form niya, yung mukha niya dapat maging makinis, yung maging maayos yung mukha or balance dapat yung mukha ng ating airplane. Kaya kapag ipinapalipad na siya sa ating himpapawid is maayos yung kanyang paglipad at nababawasan yung kanyang drag, kaya walang nangyayaring masama. Next is the surface smoothing. So refers to the process of reducing or eliminating irregularities, roughness, or sharp edges of the surface, resulting in a more even and uniform appearance. So yung ating surface smoothing daw ay makikita ito sa isang airplane. So, in-example natin kanina yung ating airplane. So, makita ito sa ating airplane. Na, nakita natin ang shape ng ating airplane is parang kalbo yung nasa taas niya. Diba? Kalbo naman talaga yung shape or yung mukha ng airplane. So, in that way, pinaprocess ang pagbawas o pag-alis ng mga magagaspang o matutulis sa gilid at pati na sa ibabaw. So, yung mga gumagawa ng mga airplane or ginaayos talaga nila nga wala may mga gaspang-gaspang sa airplane. Wala sang ginabawasan nila dito ang ng airplane. Yung parang pangit ko ng itsura ng airplane ganun. Parang ginapakinis nila kaayo para mas in that way as para kung ano na siya sa himpapawid is smooth na yung kanyang paglipad. So ginapatulis ginakuha yung mga magagaspang at matutulis sa gilid at pati na sa ibabaw. So ito yung mga techniques kumbaga ito yung mga techniques ng mga gumagawa ng mga airplane kung saan there are conduct talaga ng mga process kung paano mapapanatili na ma-reduce ang drag ng isang airplane. So, yun yung mga way nila para ma-reduce yung drag daw ng ating airplane. Kaya, ginakuha nila or ginapaganda nila yung airplane. Kaya, ang nagiging mukha ng ating airplane is pantay at pare-pareho ang anyo at hugis na meron ang bawat parte ng isang airplane. So, di ba nakita natin ang airplane is maganda na yung itsura niya, pantay or balance yung paggawa sa isang airplane. So, di ba kaya nga di ba kapag pinapalipad na siya is maganda yung flow ng ating airplane kapag nandun siya sa himpapawid. So, we have the example also which is the rubbing sandpaper on a rough piece of wood to make it smooth. Applying a smoothing cream to skin to make it feel softer and more even. So, yun yung kanyang example sa surface smoothing para maging smooth yung ating flow kapag nandun na siya sa himpapawid.
Okay, everyone, let's proceed to the types of drag reduction techniques. Active flow control system. Use internal energy input device to manipulate, control, or flow, aiming to alter the flow state or development path for improved performance, such as delaying separation or successions. Ito yung gumagamit ng enerhiya upang manipulihin ang daloy ng hangin sa paligid ng isang sasakyan na lumilipad katulad ng airplane. In active flow control system, we have dynamic spoiler. These spoilers can be deployed at high speed to spoil unwanted airflow in channel 8 in a way that reduces drag. Ito yung makikita sa likod o yung sa ulihan good ng airplane or car. Siya yung nagmamanage ng speed. Siya yung nagko-control upang maiwasan yung paghila ng hangin pababa. And we have moving flaps. Flaps can be moved to alter the shape of an object and reduce drag certain speed. Can be moved o mag-iba yung shape ng object ay nagre-reduce ng drag at siguradong bilis. We have other techniques. We have wheel covers. Wheel covers, this can help reduce the drag caused by the wheels and tires. Vortex generation, this small device can create vortices that delay flow separation and reduce pressure drag. Underbody covers, they can reduce drag by smoothing the flow underneath vehicle. Dimples, similar to vortex, generate dimples can create vortex that delay flow separation and reduce pressure drag. And we have superhydrophobic surface. This surface can reduce drag by allowing a thin layer of fluid to slip over the surface, reducing frictions. Compliant casting. This casting can deform under pressure, allowing the boundary layer flow more smoothly and reducing drag. Additive drag reductions. Adding polymers of other substances to fluid can reduce its viscosity and thus reduce drag. Bionic mucus drag reductions. Studying the drag reductions properties of speech mucus to develop similar casting.